Okay, so in this chapter we're going to be studying a little more about other ways you can use integrals. The first one is very similar to how we originally introduced integrals, and that's areas on graphs. But this time, instead of always finding an area between the graph of a function and the x-axis, we're going to be finding the areas that lie in between two functions, in between two curves on the graph. So say we have something that looks like this. We have two curves, f of x and g of x, and we want the area in between them from x equals a to x equals b, say. So we want the area of that region that's labeled S here. So if we were going to estimate the area or approximate it, just like we did when we were starting to talk about integrals, we would divide it up into a bunch of rectangles, each rectangle approximately the area of a little curved region, and add up those areas. So the width of each of those rectangles we would represent with a little piece of x, delta x. And each height we could find, instead of the height being f of some particular number, it's the difference between the two y values, the higher y value and the lower y value. So it's the upper y value minus the lower y value, and that gives you that height. So we multiply those two things, and that's the area of one rectangle, and then you add those up, right? So we have f of x minus g of x, or upper y minus lower y, times delta x. The total area of those rectangles, then, you would get by adding up those height times widths, right? Remember the sigma there means add up for each rectangle. But that's just an estimate. To get the exact area, not an estimate, we do what we did before, which is use more and more and more and more rectangles, and end up taking the limit as the number of rectangles approaches infinity. So we will have a limit, as the number of rectangles in approaches infinity, of this sum of height times width, upper y minus lower y times delta x. Well, anytime you have a limit of a sum like this, where everything's multiplied times delta x, that's an integral. Right? It's an approximation where the number of approximating slices goes to infinity. So that's equal to a definite integral of the upper minus lower y's dx, and then from x equals a to b, because that's the region we're interested in this picture. Okay, let's just write that again. So we have upper y and lower y curves. To find the area between them, we compute this integral. And a is the leftmost x value in the region, and y is the right-hand x value in the region. So that's a to b is the interval that includes the region. Okay. So I think you shouldn't memorize this formula, but I know a lot of people like to memorize or write these things on their note sheets. But what you should think about is we're slicing that area up really thin into tiny rectangles. What do those rectangles look like? And then the height times a dx is the thing you want to integrate. Okay, so a couple of things. Sometimes when you're doing this, you're not given the a and b, the left and right hand endpoints. Right? So say you want this region here between these two curves. What are a and b? Right? Well, they're the points labeled there, the left-hand edge and the right-hand edge of the region. And that's the places where those two functions intersect each other, because that's where the region ends. So you would find the points of intersection. And to do that, you'd be solving the equation where the two functions are equal to each other. You solve that. In this case, it would probably have two solutions, x equals a and x equals b, and then you found them. Also, if you don't have a graph, you might not know which function is the one below and which one is the one above, the lower and upper functions. So once you know your a and b, once you know the interval, you want to choose an x value in that interval, in that region, and then you can just stick it into both functions and see which y value is higher, and that's the upper one. Okay, so let's do an example. We're going to find the area of the region enclosed by that. One curve is y equals x squared, and one curve is y equals 2x minus x squared. Both of these are quadratic, so they're going to be two parabolas, one right side up and the other upside down. So we're looking for that region. Okay. To do the integral, I need to know where the region begins and ends in terms of x values, and I need to know which curve is upper and which is lower in that region. So first we find the points of intersection by setting x squared equal to the other y equation, 2x minus x squared. Move everything to the left, factor, and we get x equals 0 and x equals 1 are the two x values. So the left-hand x value is x equals 0 and the right-hand x value is x equals 1. Now I need to know which curve is on top. Now from the picture it looks like the 2x minus x squared is on top, but just to be sure, we're going to find the upper curve. So pick an x value in between the numbers we just found. And if we plug it into y equals x squared, we get 1/4. And if we plug it into the other equation, y equals 2x minus x squared, we get 3/4. That one's bigger, so that's the upper function in this region. So that means if I want to find the area, the height of the area at any point is that upper y value minus the lower y value, and then I will integrate that with respect to x between the two x values I found. So that's the integral from 0 to 1 of the upper thing, 2x minus x squared, minus the lower thing, x squared, with respect to x. And then this is just a little bit of simplification, very easy integral. Evaluate it, x equals 1 and x equals 0, and subtract, and we get 1/3. The area enclosed by those two curves is exactly equal to 1/3. Okay. That's not the only way areas between curves can look, right? What if the region looks curvy on the left and right, so there's not a set x equals a and x equals b? Well, sometimes you want to use horizontal rectangles instead of vertical ones. So here's an example. We have two curves. Now these are not functions where y equals a function of x. It's the other way around. X equals a function of y. All right, these would fail the vertical line test, so you have to switch the roles of x and y. So what's going on here? A little approximating rectangle would have height delta y, right? A little tiny bit in the y direction. And its width would be that right-hand value minus the left-hand value. But then after that, it's the same. If you add up those things all the way along the region, you would get the total area of all the rectangles like that. And so then when you take a limit, you would get this integral. This is an integral with respect to y, right? So it's a dy integral. That means I'm integrating up vertically instead of horizontally. That means the rectangles were teeny tiny in the y direction and bigger in the x direction, horizontal rectangles. But you do it exactly the same. The xr will be whatever x equals on the right, and that's some y stuff. The xl will be whatever x equals on the left, that's some y stuff. So you subtract them, you have y stuff. Integrate with respect to y. And you do that from the lower y value in the region up to the top y value in the region. Sometimes you might try to find points of intersection and go, oh, hey, there's 3 points of intersection, or maybe more. So it might look something like this, right? If I want to find the total area in there, what can I do? Well, the total area shaded there between f of x and g of x would be the integral from a to c of the upper y value minus the lower y value, right? Same rule. The left-hand x value is a, the right-hand x value is c, so I do the integral from a to c, and then upper minus lower y values integrate with respect to x. Sure, no problem. Except that sometimes in that region f of x is the upper y value, and sometimes g of x is the upper y value. Right? So you actually have to split it up. Right? The integral from a to c we know by the additive property I can do the integral from a to b and then add the integral from b to c. That will cover the whole area. So I can go from a to b, and in that region, f of x is the upper function and g of x is the lower function. Plus, going from b to c, g of x is the upper function and f of x is the lower function. And if you didn't know that, if you didn't have a graph, you could plug in an x value between a and b to see which one was upper there, and then plug in an x value between b and c to see which one was upper in that region. So you just have to do two integrals here. Okay. And, of course, this same sort of thing can happen if you've got functions x equals a function of y, so it sort of would look the same, but vertically. And then you'd be switching the roles of the right and left functions. Similarly split it into two integrals. Okay, so this is just the intro into finding areas of all sorts on graphs, and we will be looking at a lot of examples in class. I will see you then.